Hello, everybody. My talk will be about, the title of my talk is Music Instruments with Extra Fiber. And so I will talk a little bit about my journey in composite materials that I have taken in my research. And we will go everywhere from theory to practice. This is part of my PhD, which is a PhD in art. So not necessarily a PhD in science, but as you will see, I use quite a lot of scientific methodologies. But also the art is an important part of the research, and I will talk more about that towards the end of the research. There are two main partners of the research. So the musical instrument making department of KOSK and Conservatory Ghent, and the material science and musicology of Ghent University. I am funded by the FWO. Besides the two main partners, I also have received some support from the Poznan Conservatory, who helped with the beginning of our modal analysis. And Claudia also helped to do some analysis and do some measurements in her lab in Paris at the lab. First, a little bit of an overview about what I will talk about in the upcoming hour. First, I will introduce the topic a little bit, why I do what I do, maybe why it's interesting for you to listen to it, what we can learn from it, maybe so my motivation to do it. And then I will go over in the 1 hour over 4 years of research. So I will have to condense it a little bit. I will talk about material properties. I will not go into detail too much because already Iris and Romain mentioned this in more detail. So I will try to keep it brief. I will show you also how I make violins and cellos from composite materials completely by hand. So the idea is that if any of you violin makers want to make a composite violin or cello or other instrument, that you could base yourself on the method that I have used. And then, of course, I have made some violins, some cellos, and I wanted to learn more about them in my research. So I did some tests on them. So we did measurements, vibrational analysis, so modal analysis, and the acoustical properties we have measured. You can do, of course, a lot of tests, but we also want to know what listeners and players say about these instruments. So we did some psychoacoustic tests as well. So I will talk about those. And then in the end, I will talk about more the artistic side of the research. And so in that, we actually tried to use all the insights about actually here the material properties and how they in theory affect the sound, the things that we've measured, how these material properties change the properties of the violin, and then some insights that listeners and players have given us. And we synthesize all of that into the making of 3 cellos, one from carbon fiber, one from flax fiber, and one from glass fiber. And they were made towards a specific sound color. I will share you in the end where you can listen to them yourself. And you can be the judge if it was successful or not. I leave that totally up to you. If you see behind me, maybe if you see the screen, you already see the 3 cellos. So it's a glass fiber cello, carbon fiber, flax fiber, and then you see maybe a wooden one as well. So, but that's more towards the end of my talk. So some context. So I'm a researcher at the musical instrument making department of KOSK and Conservatory Ghent. We are an instrument making school academically, but of course also with a practical side. So we get a lot of theory, a lot of research, and our students make instruments, a very wide range of instruments. So from keyboard instruments to wind instruments to boat instruments. So not just violins, but actually a very wide range of instruments are made in our department. So introduction, Jim Woodhouse said, I don't know if he's here, in a publication, he wrote that if a violin-shaped instrument were to be invented today, wood would be the obvious choice of material given the huge range of artificial materials now available. And that's actually an interesting question. In the design world, they say that the Eames, they were famous designers, if they had access to carbon fiber, they would be working with carbon fiber. So maybe we could ask the same question. Maybe if the old masters, Stradivarius, Guarneri, if they had access to other materials that we do today, maybe they would not have used spruce, but maybe they would have used carbon fiber or some different material. So the idea is that I want to investigate just very out of the box, what is this idea? And if we use a different material, what does that do? How does that change the sound and the properties of the instrument? So the idea is very much an artistic one. And he says also that a very simple criterion can be used to derive a crude index of merit for materials, and that is to seek a material that allows the loudest sound to be made for an instrument of a more or less conventional sound, design. Now, this is, of course, a crude index of merit. As every violin maker knows, not only the loudness of a violin is important, also the playability, the balance, and especially the sound color of an instrument. So it is very crude, but it gives us an idea on where we need to start when we look into maybe some different materials. This is also a little bit, why I think it is interesting, because it's very out of the box to use very different materials. And we can gain a lot of insights actually about conventional materials by doing something very strange, very different. So the goal I want to emphasize of this research is not to mimic the sound of wooden instruments. A lot of research on alternative materials, they try to make carbon fiber instruments and make them sound like wood. That's totally not what I try to do. I just say I want to make a violin-shaped instrument or a cello-shaped instrument with different materials, and I just want to study how do they sound. What do we measure? What do people like? What do people not like about the instrument? So very much open-ended. So not with the idea of ending up somewhere specific. So any research starts from a few research questions. So at the start of my PhD, I listed these 4 questions to focus on. So first, I wanted to know what alternative materials have good acoustical and mechanical properties. Good is, of course, very subjective, but there is quite a lot of research on material properties, also on wood. Iris and Romain talked about this, that give us some idea of what materials are better suited than others. Then follows the question of the violin maker. How can these materials be used in musical instruments? Of course, you can say carbon fiber or maybe some metal or maybe some different material is good, but how do I, a violin maker, actually make a violin out of it? So I want to use my craftsmanship, my knowledge, to really craft an instrument. How do I do that to make an instrument that works? Then the next is I have made by then a couple of instruments. And so I want to study them. So I want to measure their physical properties, how they move, how they vibrate, and how they radiate the sound. But also I want to see more their artistic properties. How do listeners describe their sound? How do players describe the sound and the playability? So we get a little bit of that. And that already is a little bit of a bridge towards the last research question, which is then what place or function can these instruments have in the music and art world? Of course, we have our wooden instruments and they have a very set place already, but these new materials, they are new. We have a lot of musicians and composers which are interested in them for different reasons. So I want to investigate what could be the benefit of these new materials, what place could they have besides wooden instruments. So not to replace them, not at all, but just something different. So first I started actually by looking at research that goes into woods and that says why certain woods are used for soundboards. And here is a paper by Recht that describes actually many wood species and what they are used for. And in general, you could say that in Western instruments with soundboards, we look for woods. Here in the horizontal axis, you have the density. So with a low density, a low weight material, and here a high speed of sound, or also sometimes a high stiffness is used. And so you see here that these are the soundboard materials. To the left already here, you see that balsa is actually quite close to that. So that is a reason why some makers experiment with balsa as well. Here you have a dashed line, and that's a theoretical sound radiation coefficient. I want to emphasize the fact that this is a theoretical thing. And the idea is that the further away from this line, the better a material would be at radiating sound or in a soundboard. So as we will see, this is a little bit simplified, but I will come back to that in a second. other properties that we can investigate are the damping of a material. Some papers say that maybe we need a low damping, because if you have a lot of energy loss within the material, yeah, that energy cannot be transferred into sound. But then other papers say, yes, of course, but when we varnish a violin, we actually add damping to it. So perhaps a little bit of damping is good. So with the damping, we're not so sure. Do we want more? Do we want less? What's the idea? And then also an important property is the anisotropy of a material. And of course, woods, they are usually anisotropic. So this means, of course, if you have a normal plate, that you have all the fibers of the wood running in one direction, and in the other fibers, the plate is, in other directions, I'm sorry, the plate is a lot more flexible. But when we look at composites, it's not necessarily the case. Here, I have a plate with fibers also running in this direction. So composite materials give us some options. So we have to see what the effect of that would be. Here I took then that idea from those wooden materials and what makes them suitable to an overall material overview. So again, here you have on the horizontal graph, the density. And here on the vertical graph, the speed of sound. Again, this dotted line is the sound radiation coefficient. And here in the dark green, you see all the natural materials, including the woods. Here, these ones, that's balsa wood, and spruce is somewhere over here. This is spruce in the longitudinal direction, so in the direction of the fibers. But of course, a soundboard is not just one direction, it is two. And this is something that Romain always emphasizes, that we have different flexibilities in our material and we have to account for those. So if we, for example, look at spruce in the longitudinal direction, it's here. But if we look at it in the transverse direction, so across the grain, 90-degree angle, it is here. So the acoustic behavior of the plate will be somewhere in between this for its sound radiation, because of course both will have an impact. So, okay, we know that we don't want to go too far away from this dotted line. And the more higher we go here, in theory, the more of an efficient sound radio we have. So here below, you have the rigid foams. And as you see, foams are a very wide category. But here you have the rigid foams, like for example, styrofoam. So as you see in theory, they're actually very good sound radiators. And that's actually quite normal. In Dutch, we have a name for styrofoam, and we call it piepschuim. So it's a squeaky foam, translated to English. And I'm sure you all know this when you unbox something, that it makes a lot of sound. So styrofoam is a very good sound radiator. But of course, we also know that these foams, they are very, you can easily damage them. So they're not so durable. So we want to look towards more durable materials. And then here at the upper end of the density, you have the composite materials. And so in theory, they are quite good as well. So they are more dense, they are heavier, but they are a lot stiffer and they have therefore a higher speed of sound. When you see metals and alloys, they're, let's say in general, too heavy to make a soundboard from in theory. Elastics, of course, they're not useful at all. And here you have the plastics group of materials. Also here, I want to just mention the damping. So for example, you have flax fiber, which is a natural fiber. It has a higher damping than carbon and glass fiber, which are man-made materials. So it depends a little bit on the fiber, what the damping is. Also here, the orange dots that I have added are some, man-made materials which go a step further, and they are sandwich materials. So it's not just one material, but you combine a few of them together. And in this case here, you see that it is a 0.2 millimeter thin carbon, so very, very thin, combined with a core of styrofoam of 3 millimeters thick. So you get two very thin carbon fiber pieces, and there is a core which makes it very lightweight. And those materials, in theory, are very good sound radiators. And actually, it's something that guitar makers already do. They often call it double tops, and they often use spruce on two sides in combination with a lightweight core which is often a Nomex honeycomb material, or balsa sometimes. So this is not a new concept to instrument making, but in violin making, it's not done very much. So these fiber composite materials, fiber reinforced composites, are in theory interesting, but what are they exactly? They are a combination of two materials together. You have a very, very strong fiber, which is in this case here, carbon fiber. And you see that it is woven in two directions, and it's combined with the glue. And the carbon fiber is extremely strong in tension. So you can pull it and it will not bend, will not stretch a lot. But of course, in compression, it's not very well suited. So you combine it with a resin, and then you get actually a new material in which the fibers and the resin, in my case epoxy, work together to form a really durable, strong and stiff material. So why are they interesting in theory? They have a good stiffness to weight ratio. Because of that, they are now used more and more in planes and in Formula 1 cars, and so in a lot of high-end applications. They have a lower damping. I put lower between brackets because, as you saw, it depends on the fiber. And they have an adjustable anisotropy. So this means that I can put the fibers in any direction. So in this plate, it was into two directions. But if I want, I can also use carbon fiber, which has all the fibers in one direction. So actually I can choose. So it gives me options as a violin maker. So for me, this is interesting. And of course, it's a very durable material. A curiosity, wood is actually also a composite material. So if you're feeling a little bit anxious about fiber reinforced composite materials, if you're a violin maker, you've been working with it for years already. So we always think we are so smart, but actually Mother Nature was one step ahead of us. And so in wood, actually, you have cellulose fibers, which are very stiff, and they are held together by a matrix, a glue, a resin, you could say, of lignin and extractives. And so those two work together to form the amazing material called wood. So now, okay, I want to make music instruments from these fibers, but where do I start? You have a lot of variability. Some fibers are stiffer than others, so I need to make some calculations, need to do some things. First, you have, of course, the issue of the fiber orientation, so the anisotropy of a material. Here you see two instruments, a guitar and a ukulele, made by the same company. And in the guitar, they put all the fibers, these are flax fibers, in one direction, while in the ukulele, they put the flax fibers in two directions. So as a violin maker, you might intuitively understand that this will be stiff in one direction, while here we have stiffness in two directions. So, of course, when we are making just a wooden top plate, we shape the thickness and we feel it, how stiff it is with our hands, we twist it, we turn it. But with these composite materials, that would be a lot of trial and error to end up at a good plate. So I calculated it. So engineers, they use something called engineering constants. And actually they calculate this bending stiffness that we use as violin makers with some formula. So for example, here you have for the longitudinal direction, a simplified formula, and it's E is the stiffness of the material in one direction. H is the thickness of the material. So you see it's to the third power. So the thickness has a very, very large influence on the stiffness of the plate, divided by 12, and then M. And M is a derivative of the Poisson ratio. So it's a different material property. So for example, if we take a spruce plate of 2.5 millimeters, and we calculate the engineering constants, we have this. So very stiff in the longitudinal direction, the 11, and a lot less stiff in the transverse direction, which is this, and then also in twist. So D66 is actually torsion. So if we take a plate like this and we torse it like that, that's actually this D66. When we change to a different material, flax fibers, for example, and we put it all in the unidirectional way, so the fibers are similar like this guitar, we actually end up with a different thickness, but we can make actually the stiffness in the different directions comparable to each other. If we use woven flax, however, we end up with a stiffness which is a lot higher in one direction. So you see that if we change these fibers and the fiber orientation, that we will change the behavior of the plate. So interesting to take into account. If we go to carbon fiber, for example, this is carbon fiber, which is unidirectional. It is a very, very stiff and strong fiber. So we need to make it a lot thinner, so almost a little bit over 1 millimeters, to have the same strength and stiffness, well, the same stiffness, not strength, the strength will be higher, as the spruce plate here. And then you see that the stiffness in longitudinal direction is similar, also in the transverse direction, but the torsion of the material is a lot lower. So a carbon fiber plate is very easy to twist like this. So it is different from wood. Of course, you can try and manipulate them to be more alike, but that was not my intention, so I kept it like this. Of course, you can also use carbon woven, just like here in the flax fiber, fiber ukulele. And then you can also manipulate this, so then you have stiffness in 2 directions, but still the torsion is low. So depending on how you orientate the fibers, you get a different soundboard. So I know a little bit about these materials. I know that some materials are more stiff than others. The fibers can make a difference, but how can I, as just a conventional violin maker, make instruments from these materials in a way that I can use my knowledge of the craft? So the idea here was that I didn't want to use 3D software because in 3D software, it's very difficult to make a very good arching and shape that I want. So I really wanted to shape the instruments in a more or less conventional way. The idea behind it was that any of you who would want to make such an instrument could do so quite easily by copying my methods. I will share this in a video, which will be about 5 minutes in a minute. But first I will discuss the most important steps. So first I carved my entire instruments from a PU foam, about density about 250 kilograms per cubic meter. And as you can see here, you have like the little shavings that you also have with wood. So it works in a very similar way to wood. You have no grain structure, of course, but you can shape the cello or the violin in a very conventional way. Then on those patterns, I put the glass fiber molds. So glass fiber and polyester together, they harden up, they become a composite, and they become very stiff. And then that mold I can use to make actually my composite materials into directly a product. So I put the fabric here inside the mold. So this is carbon fiber fabric, just a loose one. It goes under vacuum. And then under vacuum, the resin infuses the fabric, and then it hardens. And when it comes out, it is a solid material. So I will show you here the video. It's about 5 minutes. And it will show the complete making of a cello from carbon fiber. Some of you may have already seen this. The music that you hear was actually recorded on this carbon fiber cello. And it's based on a composition of a composer who actually composed it then on this video. So the music is adapted to the video. So that was how I made a cello from carbon fiber. This video, along with 3 separate videos which go into more detail, you can find on YouTube. So if you want more information on how exactly I made it, if you have questions, you can ask them also there, and I try to answer them on my YouTube channel regularly. Oh, that we've done. So that's how I make the violins and the cellos. But let's first go back to the violins that we've made. So I wanted to only change the soundboard material, the top plate. So the other parts of the instrument are all carbon fiber. So the sides, the back, the neck, they are all the same. They're all carbon fiber, but only the top plate is different. And so I made 6 violins. One I made 2 times, which had this one, twill CA and twill CB. They have a unidirectional carbon fiber inside, but the outside is a woven carbon fiber. You have unidirectional carbon, so all the fibers are in the same direction, or almost all the fibers. You have UD flax, so this is unidirectional flax fibers. And then you have a sandwich material. So this sandwich material is actually the combination of a very thin carbon fiber sheet, 0.2 millimeters, together with a core material, which is in this case a Nomex honeycomb, and that's about 1.5 millimeters thick. So these are all calculated and made to have the same stiffness along the axis of the instrument, but because there are different materials, the end result, the weight of the soundboard, is very different. So here you see, I also made one, I'm not sure if you can see this, maybe I have to shift this down. I also just made one reference, spruce soundboard. So just so you can compare it. So it's, let's say on the heavy conventional side, 75 grams. But so the composite materials, the unidirectional flax, you have to add a lot more for it to be stiff enough. So you end up with a very high weight, 100 grams for the top plate. The unidirectional carbon and twill CA, they are about 72, 71 grams. Twill CB was a little bit more. So you see that with this method that I have shown, the twill CA and the twill CB, I have tried to make them the same, but they're not completely identical. So there is a minor difference between the two. Of course, if you would further industrialize the making process, probably you can reduce this. But for me, that was not so much the point. I wanted to see, using my method, how precise it was and what the variability was. And then here also you see this sandwich material, so the carbon fiber and the Nomex being incredibly lightweight, so 42 grams for the top plate. That's including the sound holes and bass bar. So for all of these instruments, it was the weight of the soundboards just before they were glued. The ends were trimmed off a little bit, so it could be that the end weight is a little bit lower than what's here, but it will not be so much. So like this, I have made 6 violins. And I wanted to see now if we can see the effect of the weight, of the different anisotropy, of the different fiber on the instruments, and if we can measure the change. And so first I did a modal analysis. We did it in a non-contact way. So this method has been used by Romain previously with a speaker to excite the instrument, and then the violin is before it, and you measure the output, the vibration of the instrument with the laser Doppler vibrometer. I will not go into detail too much, but so the idea is that you let the instrument vibrate and you measure the response. So you get the frequency response function of the instrument, and that allows you, together with a certain software, which was Polymax, to then identify the signature modes of the instrument. So these modes have been talked about in other presentations, so I will not go into detail too much. But here I have a small video. I will lower the volume so I don't scare you too much. You will hear the speaker. It makes a burst chirp signal. So it's a sort of sine wave, you could say. And it goes weep, weep, and then the laser Doppler vibrometer measures the response. It's completely automatic, so the laser changes position itself. This is the scanning head of the laser. then here you see the software, and you see that it's measuring all the points completely. So the idea why we did a non-contact modal analysis, of course, most of the time this is done using an impact hammer as an input signal. But since our school has a lot of historical instruments that we want to study as well, we wanted to see if it could be completely non-contact. So that, for example, if you have a very old violin and the owners do not want you to touch it with an impact hammer, or you have a violin which has no bridge that you can tap on with an impact hammer, that still you could use this method. And actually, we have good measurements with it. So then you see the signature modes, and they change in frequency due to the material properties. So that's already a good sign that we're measuring the material properties, we change them, and we can see it in the measurement. So that's already good. Here at the top, you can see the modes. And here we have the A1 mode. We're not really sure if we should call it the A1 mode, because actually here you see that it changes a lot in frequency. And the A1 mode should be an air mode mostly, but that's for a detailed discussion, which maybe we can have after the talk. But you see here, for example, this is just a signature mode. So the A0 is below here. And you see that for example, UD flax, which is the lowest stiffness in the longitudinal and transverse direction. So it is very flexible, and it is the highest weight. So this was 100 grams. It has lower frequencies for the signature modes than the other violins, followed by unidirectional carbon. So the fact that it's unidirectional makes, again, the frequencies lower, but because it has less weight, it's a little bit higher than the flax violin. So these are two unidirectional ones, heavier one and more lightweight. Then you see the 12CA and the 12CB. So these had a little bit higher stiffness in the transverse direction. So in this direction, it's a little bit stiffer. And you can see that in frequency, their modes are quite close to each other here, the A1, the B1 minus, the CBR, and the B1 plus. But in amplitude, there is a small difference. But they are definitely more alike than all the others. So that's good. Also, we have here spruce. So the spruce top plate, we just added it as a reference. So it's around here. And then the sandwich material, which was, as you remember, very lightweight. So 42 grams and very stiff because it has the fibers in two directions. It has a lot of higher frequencies than the other violins. So here we see the A1 is the highest, the B1 minus is a lot higher than the other ones. And here also the B1 plus is slightly higher than that of the other instruments. If there are questions about this, I want to go into detail with that after the talk, because I want to keep an eye on time and make sure that I can discuss some other things as well. So then, of course, you have the vibrations, but we want to know also how do they radiate the sound. And that we do by using a developed method, which has been used by many colleagues of you and has been developed by some people listening here. This is a rig which has been sort of developed by Joseph Curtin. The idea is you use an impact hammer to excite the instrument and you measure the response with a microphone. He uses the OBI app software, which is made by Chris Rogers. And these measurements are then also, and the software is based on a lot of work of George. So there are many, many people that come before me that did these kind of measurements and have contributed to making these kinds of measurements work. And so here you see one of the violins in the LAM lab in Paris. So this is an anechoic chamber. And there we did the tests. And here you see the response. And you see that they are very different between the instruments. We also added a conventional violin. So it's just a normal modern wooden violin, just as a reference for you. And so you see that they are very different. Let's look at the extreme examples. So the sandwich one was the very lightweight top, so 42 grams. And here it has the lowest output of all the violins. But here between 380 and 3000 hertz, it has a lot of a higher response than the other violins. Above 3000 hertz is more or less in the middle again. If we look at the other end of the spectrum, the UD flax violin, so unidirectional and heavyweight, Here it has a high response, and then it has the lowest response of all of them. So these two are the furthest apart. And so when we want to examine the sound of a composite material, we immediately see that it depends very much on which material you use. And so flax fibers or carbon fibers, a core or no core, it makes a huge, huge difference. So there is no such thing as the sound of a carbon fiber violin. It depends very much on how you make the carbon fiber violin or the flax fiber violin, etc. I want to quickly zoom in a little bit and compare some violins. So here you see 12CA and 12CB. They were made to be the same. They were not exactly, but as you can see, their response curves are quite similar. So the A0, the A1, the B1 minus is very high. The CBR is around here. And then the B1 plus is actually quite low in radiation. This is due to we found through modal analysis, to a lot stiffer sides. So because we use carbon fiber in the sides and they end up going through the back plate, it is very, very stiff. And therefore, apparently, it affects the radiation of the B1 plus mode. So we found that to be the case. If we compare 12CB with the unidirectional carbon, you see that the modes shift down a little bit. So as you make it more anisotropic, the plate, the frequencies go down. Same is the case for unidirectional flax and unidirectional carbon. So as you increase the weight and the different fiber, the frequencies go down again. Then here, the sandwich, the extreme one, you can see it has a very high B1 minus mode. And here also you see the output that I've shown previously. So according to these measurements, if you're familiar with looking at FRF curves of instruments, these instruments should sound very, very different. They are very wide apart. But of course, the question then is, do we perceive these sounds to be different? We can measure everything we want. And in fact, this has been done a lot with old violins, that we measure all the details. But then Claudia has shown that maybe we don't perceive the difference. So it's very important that we do listening and playing tests. And we do them blind. So I will go over to that. So we did some perceptual tests. First, we did 2 blind listening tests. These were published. So if you want, you can check this out. If you want the full article, just send me a message and I will send it to you. So this consisted of 2 tasks, an evaluation task, where we had only 1 player, but we had 37 listeners. And then to confirm these results, because there were a little bit of strange things going on, we did a second test with 2 players now, and then 40 listeners. So with these results together, we have already an idea on what the perceived sound is of these instruments. I will go into detail a little bit about the results in a minute. And then also we did 1 blind playing test. So apart from that, there we had 33 players who participated, but unfortunately we only had 4 professionals. Why we had only 4 professionals? The issue was that for this test, we wanted players who never played or heard the instruments before. That all of them would have a fresh, blind view. None of them would be biased. And of course, we used some of our players before here, and most of the professional players around this area that were interested in these violins already came before the test to try them out in my workshop. So maybe I made a mistake there of allowing too many people to play the instruments before. So we had a little bit of trouble to get more professionals to participate in the research. But so we do what we can. So some results, this is from the publication also. So we asked the participants to list actually the sound of the instruments individually on a Likert scale. So between a certain scale from warm to cold or from loud to quiet. So we had all these adjectives. And from this then you can derive the mean score of the group and the statistical variation within the group. So the dot is the mean and the line is the standard error of the mean. So the variation, or of course there are people who voted here and who voted here. Right? This is just statistics. And then based on this, you can say if there is a strong evidence or a weak evidence that the group, the mean, goes to one certain direction. So towards warm or towards cold, for example, here. And here you see that the green dots, they have a strong statistical evidence for it. that these instruments are perceived as warm by the group. And then here, 12CA, the second time it was presented, had a weak evidence. As you can see, 12CA was presented 2 times in the research, unbeknownst to the listeners. So the audience did not know which violins they were listening to, and they did not know that one violin was repeated 2 times. These are the results that we have, the strong evidence, how it was perceived, and the weak evidence. Also, afterwards, we asked the audience if they had an overall preference, which violins sounds that they liked more and less. And here you see 2 favorites, 12CB and UD flax, and one which was clearly the least favorite, which was the sandwich violin. And that's interesting because in our theory, we thought that the loudest violin should be the best violin. And here we see already that the listeners do not agree. So they say that this violin was the worst. So we have to dive into why they think that is the case. Of course, in this research, we saw that there was a difference due to the order effect. So the order in which you present the violins to the audience affects their judgment on it. So here you see 12CA, the first time we had strong evidence that it sounded dim and then loud, close, and bad. And then the second time, it was loud, sharp, and powerful, and warm, clear, good, nasal, and bright. So apparently we had a huge difference the first time, and the second time the instrument was heard. So this is especially interesting for example, violin making competitions, that actually the order in which the instruments are presented affect how we judge them. So that's important to take with us. So that's why we did the second test to confirm some of these results. But first, I will go into what our listeners found important. So we also asked them, what pair of words do you think is most important to judge the quality of a violin? And then rich and poor were chosen most, and powerful and weak were actually not chosen that much by that many participants. So apparently the sound color was quite important. And this is from the second listening test that we did. We asked a similar question. So we presented pairs of the violins and we asked, why did you favor one violin? And most said that they favored the violin because of its sound color, followed by its projection, then its balance. If they chose sound color, they could also indicate why. And so this is what you see here. Of course, I must add that all of these tests were in the solo condition. So all of these judgments were of a violin in just solo condition. So perhaps if we have a violin in an orchestra or in a quartet setting, the audience will put a different emphasis on it. So that is important to take with us. But what about the players? So we also did the playing test, and we actually see the same trends as in our listening test. So, for example, the sandwich violin, we asked the players to rate sound color, projection, playability, and response. And we see that the sandwich violin was really not favored at all because of its sound color. So we can see how they describe the sound color of this violin. And so they said it was sharp, loud, nasal, harsh, powerful, but apparently the sound color was not favored by the players. Overall, we also asked them about the projection, which is here strange that the sandwich violin has a low projection in comparison to some of the other violins, because in theory, it should be the best projector. And also our listeners actually said that this was the best projecting and the loudest violin. So here again, we do see that the sound color of UD flax, for example, is favored over the other instruments overall. And 12CB is close to it. So flax, for example, then was described as warm, as dull, round, closed, and good. So we see that the players have a different opinion. So one could ask the question, the sandwich violin is clearly the worst. The listeners do not like it. Our average of the players also do not like it. So in our context, maybe the sandwich violin is the worst. And there I have to add, yes, but in that specific context, because as we look just at the 4 professional participants, so of course, 4 is not really statistically significant, but still it's interesting to look at how they rated the violins. 2 of them actually preferred the sandwich violin. So out of our 4 participants, professional number 2 and professional number 4 gave the sandwich actually a very high score on sound color, projection, playability, and response. Here, professional player number 3 said that he could not reliably judge projection, so he preferred not to answer that question. So we allowed him to do that. And actually, funnily enough, professional player number 4, you see she gave a very high score to the sandwich violin. She actually asked after the test if the instrument would be for sale and if she could buy it. So that's a funny thing, that in our listening tests and in most of our players, this one violin was the worst. But then when we ask some professionals, actually they favor a different instrument. And they're actually interested in it. So the answer is that the question of what is a good violin or what is the best violin, it is very subjective. So what is the value of these insights? For me, I think I have learned that there is no such thing as the best instrument overall. It really depends on the context. And of course, if you have a violin making competition, maybe you strive towards a certain sound. But the music world is a very big one. The classical music world even is a big one. So there's nothing to say that one violin would have the best sound for each and every performance and for each and every musician. So it's okay for instruments to sound different. And in fact, I like instruments to sound different. So that's my personal opinion. So to round off this research, I said it was an artistic research. So we really wanted to synthesize some of those insights into using those materials, those composite materials towards a certain sound. So we did that by making some cellos. Before I go to them, I just want to repeat. So there's a YouTube videos where you can check it out. And if you have questions, you can contact me. We can discuss later, of course, but you can contact me also here or ask me on Facebook. But so now I can end the screen sharing. Stop sharing. Okay, so you see me again. And now I can go back to the cellos. So here you have a carbon fiber cello. And the idea here was that we wanted to use actually the carbon fiber, the stiffness and the strength to produce a cello which sounds very powerful, because apparently carbon fiber would be good at that. But also, like the 12CD violin, warm and round, but especially with strong A string. And so that was then this cello. I think personally, but this is a very subjective opinion, I add, that this is a good alternative if you just want a good sounding instrument, which is durable. But then, and I think this is more interesting, we wanted to go further away from the sounds of these classical cellos, conventional cellos, and we want to explore 2 very different directions. The first one was a flax fiber cello. So in this cello, flax fibers are used as well for both the backs, the sides, and the idea here was that we want to make a similar violin, similar one like the violin. So a very soft sound, a very round sound, a very warm sound. And actually this violin, this cello, I'm sorry, is very easy to play in a way. And yeah, it makes it very easy for recordings to make a beautiful sound. So it's not a very loud cello, so it's not very well suited for big concert halls. But for example, in combination with lesser loud instruments, we found this to be a good example. And then last but not least, you have sort of the sandwich violin in a cello form. So here we have a glass fiber cello, which has actually a honeycomb in between it. And I hope you can see it. So glass fiber is transparent, so you can see the sound post and the bass bar within the cello. And here I also used the anisotropy. So I put fibers in different directions to really make it very stiff and lightweight. And the idea was that we wanted a very high-pitched instrument that sounds very clear, very bright, maybe a little bit harsh, but so to really emphasize the fact that it's glass in a way. And opinions about this instrument are the most diverse. So actually, most cellists, similar to the sandwich violin, do not very much like the sound of the cello. But then when we see what cellos were asked most about by composers and musicians to use, this is the favorite one. So out of the 3 cellos that we have developed, this instrument has been used most in performances and in recordings. And I will share with you a recording after the questions, where you can actually see that a pianist and a cellist actually used this glass fiber cello and its specific sound color to really emphasize the clarity in a Japanese piece by a Japanese composer. I think I have talked a lot. Maybe I have lost some of you somewhere along the way, and probably many people of you have questions. So I have not been looking into the chat. So maybe Claudia, what are the most important questions that I should answer?
Thank you, Tim. I don't know. I think we should start with people raising questions like orally. It's more fun, and then we can go back to the chat at some point. Is there anybody raising hands? Let me look at participants panel.
Dietmar has a question, yes?
Hi, Tim.
Hi.
Why have you chosen honeycomb instead of hard foam for the sandwich structure? Because I've tried both, and the outcome with the honeycomb was very much like what you described, and with hard foam, it's a completely different thing.
Yeah, we had to choose one or the other, of course. And in our violin, first we started with the Nomex, because this has been used, I think, more by guitar makers. Huh? So there's, let's say, more of a tradition maybe already, a little bit on that. So we wanted first to do that. Also, I had some issues with, we did some tests with styrofoam, where after a while, the material started to do this a little bit. So it was not very, very stable. So of course, with other foams, you don't have this issue probably. So you have to find this foam which is lightweight enough and then also rigid enough so it doesn't shift over time. So we chose Nomex because we knew that it was going to be stable over time as well. So that, yeah, of course, many options. And I'm sure all of them will influence the sound in some way or another. So we've just barely scratched the surface here of what is possible, definitely, yeah.
And another question of mine was, you're talking about high tensile fibers when you talk about carbon fiber.
You're asking about which fibers I used? Or I used actually quite conventional carbon fibers, so not the high production market.
High modulus or something like that. No high modulus or something like that.
No. Okay. So yeah, because I wanted to also work with materials that are more easily available, let's say, so that again, any other violin maker who wanted to try something like this could do it. The same with, for example, the glass fiber. You have glass fiber out of very different qualities. I just use a conventional one. So again, here we're barely scratching the surface. And I'm sure maybe you have more experience actually working with different carbon fibers, that it will affect the sound as well, of course, definitely. But what I think I can say based on my experience is that the layup is incredibly important. So that the thickness that you have, and of course the anisotropy. So if you put the fibers in one direction or like this, based on the measurements, it affects a lot. Of course, then the question with the perception becomes less clear. So we have these very clear radiation measurements, etc. But when we go to the perception side and listeners and players, everything becomes more fluid and it's more hard to really draw conclusions, especially scientifically.
I know exactly.
Yes.
Well, thanks.
Thank you. Any other questions?
Yes, Francesco would like to ask a question.
Yes.
Yeah.
Congratulations. Very nice job and a very nice talk.
Thank you.
Regarding the 6 violins, I guess the dimension, the geometry was kept the same also with the rib height.
Yes.
So the volume cavity was this approximately the same apart from small differences from the bass bar and so on.
Yeah, approximately, yeah, yes. So not exactly, because you have some differences. Yes, you have a different model, of course. So we left away the corner blocks and we had just had the H shape. But yes, the height, the rib height was within what conventional violins have. Okay.
So I think it is very interesting for makers to see the effect of the material on a simple parameter such as A null. So, and also I was surprised to see that the heavier violins were the one that made more noise in the lower part of the spectrum, as you showed us. That goes against somehow the intuition. Yeah, it was not necessarily that they make more, that they have a higher output, but it's just because what I showed was also the band averages. And then, of course, if you have a peak which is just shifting towards the different band, okay, yeah, then it's higher. Of course, maybe that also changes in our perception. If this peak is actually lower, a couple of 20, 30 hertz, maybe actually we hear this difference. Yeah. Thanks. Thank you. Any more questions?
I have a question about the plots you showed that you did with your modal analysis system, because the radiation measurement, though they are very different from conventional violins, they really look like radiation pattern that we can see with violins, although the peaks are different and not, but with your other measurements, they look very peculiar to me. So I was wondering, what are they? Because is that like equivalent of a bridge admittance or?
What we saw was...
Could you go back? Could you maybe share your slide again?
I will see. Share screen. So what you were talking about was this, right? Claudia?
This one.
This one, yes. So yes. First of all, the range is limited here. Huh? I only showed from 300 hertz to 600 hertz. Huh? So that's already making it look a little bit different.
Yes.
Than a conventional one. Because I just wanted to zoom in here on the frequencies within the signature mode area.
But so how did you measure this this plot? How did you get it? What is
this plot was with the non-contact modal analysis.
Yes,
so
but where? Is that because it has to be in a specific position, I suppose. What you actually plot, no?
This is the average of all our measurement points.
Ah, that's the average. Okay, that's what I wanted to know.
Ah, yes, okay. So yeah, so the modal analysis, the laser measure the over 150, I don't know, points. And so this plot is the average of all those points together. Yes.
Okay, that's right. It's just because, like, you know, your B1 minus being so, the green one, or
yes,
the one, it's very funny to have such a wide peak and with wiggles and...
Mm-hmm. Well, it depends.
Because it's not something we see in the radiation measurements.
I'm sorry, what?
It's not something we see in the radiation measurement. You have some peculiar peaks here that we...
Yes. Well,
we didn't see when we made the radiation measurements.
It depends on how you zoom in on the graph also.
Okay.
And because here the range is quite small here and then wide, so the peaks seem wider.
Okay.
So yeah, because actually the damping of all of these modes extracted by the Polymax software is not so peculiar. So there's some variation, but yeah.
Tim?
Yes.
Tim?
Yes, Colin.
Staying on with those curves, you have A0 and you have A1.
Yes.
I think A1 is what we would conventionally call B1 minus, because it's a breathing mode, and that's the mode that's actually exciting the A0 resonance. But of course, you haven't got the A0 resonance there.
Mm-hmm.
And I think perhaps, I mean, it's puzzling. It has, if you go back to it, they both have much the same sort of shape. I have to see it on the screen again.
Yes.
Yeah, if we look at the top right-hand corner of the thing, you have A0 and A1, which are basically the same symmetry modes. You have to ask yourself, what's the difference? And the difference is almost that the back plate, the top upper half of the back plate, it's like a dipole mode or something like that. You've got lots of activities down here in the lower bout. Here it's in the same phase, and it's there in the opposite phase.
Mm-hmm.
So it's some structure, in fact, that's happening on the B1 minus, what I would call. Here you have got the A0 mode. So no, I would think that's the A0 mode. Sorry, that you haven't got that on the graph. That's the mode. And that is, I think, what I would call the B1 minus mode. It's the main breathing mode that's actually exciting that mode. That's why it looks like that. It has the same symmetry. I'm not quite sure what your
when you compare to the measurements
Sorry?
of the acoustic radiation, you see here that indeed, like for example, when you look at UDC, you see here these two peaks, which you would think are indeed the B1 minus and the B1 plus, and not the A1 and the B1 minus. But when we compare the shapes to the literature shapes of these modes, then we find B1 plus is more over here.
Well, it might be so, because I mean, that's associated with the bending. It may be in these materials, the B1 mode is always really quite small, and that's largely a bending mode, I think, the anticlastic bending mode. And so that all these...
I think it's the ribs that's making the difference.
Yes,
yes, exactly.
Yes, we actually did a modal analysis of the ribs also to see, because the B1 plus mode in the modal analysis here of the top plate, actually the movement, the amplitude is high. So we wanted to know, why do we have a lot of movement here, but when we go to the radiation at the same frequency, we don't see radiation. And so that is due to the sides which behave differently than normal. So on a normal violin, let me get ribs. So of course, maybe I'll stop sharing. So you have the normal rib structure. And when we did the modal analysis of a normal violin, we saw at this frequency that you have a lot of this motion, a lot of this.
Yeah.
But in our carbon violin, we did not find it at this frequency. There was some other more twisty motion, but not really this. So, apparently in the conventional violin, in comparison to the carbon fiber one, maybe this mode radiates more due to this movement, more so than the top plate, because in our carbon fiber violins, we have the movement from literature and the high amplitude that we would expect, but we don't have the radiation. And the only thing different...
You have more of the corpus anticlastic bending component and less of the breathing volume change component.
Yes.
And that's because the structure is in some way. So I think that's something you could address. You get that back if you wanted. By changing
Claudia, I think it'd be nice for us to, those of us who are interested in this, to come back to it. There are probably other people who've got other questions.
Yes, that's what I was thinking, yeah. But there were other questions in the chat, so I don't know. I mean, chat is nice. It's just like, don't jump in as well in the conversation, ask your question orally, because it's always nicer. And for the people who are going to watch the video, it's nicer if the question is asked than if Tim is reading the question, so don't hesitate. Okay, John. There is Aris and John. John. You have to unmute yourself.
Wonderful presentation. Wonderful. Can you hear me okay?
Yes. Yes.
We had a terrible storm here and our internet is very, very stable. So wonderful work, Tim, very close to home for me. And I have some questions to comment. I've done some similar work in other materials, actually based off of.
Hello?
We're still with you, but not with John.
No.
Yes.
He was talking about a big storm, so maybe they got some electricity problems.
Where's John speaking from?
Okay.
I'm afraid.
Okay, in that case, he will probably be back in no time. So let's Harris ask his question then.
Thank you. Great talk, by the way. Very informative. My congratulations. I wanted to ask a couple of things, if I may. First, can you tell us a little more about your decision on using a wooden bass bar? And second question, you showed a chart with a preference from the listeners, and in there you had the different violin models, and you had two violins that are supposedly the same, but the preference was widely different. Can you explain a bit more if you discussed with the listeners why there was this difference?
Of course. So I'll start with the first question. So why the wooden bass bar? Very good question. Because actually adapting a wooden bass bar and changing it with a carbon fiber one is without accidentally increasing the stiffness too much or causing some other behavior is actually quite difficult. So I could have made a carbon fiber bass bar, but if I would have made it then way too stiff, or there would be some variation within the bass bar, I would not be measuring the difference of the soundboards, but of the bass bar. And so we wanted to negate that. So what we did was we used just wooden bass bars, but we took all of them from the same plate. So we took a high quality shallow bass bar and we divided that up into 6 violin bass bars so that we have a more or less consistent bass bar, and that we can give it, of course, as you can see, a very conventional design, because, well, you have to limit your research in some way. And for me, the focus was very much the soundboard material and not the bass bar. And I think maybe the bass bar can be an entire research on its own, on how it affects things and what you change to it. So we wanted to not make the accidental mistake of introducing some variable that's, yeah.
Okay. I just wanted your opinion on what do you think would happen sonically, acoustically, if you had the same material on the bass bar?
Mm-hmm. Very difficult to predict. It depends, of course, if you have the same moment of inertia of your bass bar, so let's say the same weight and the same stiffness, then in theory it should behave rather similarly. But of course, well, probably you will change one or the other. And then you're likely to affect the modes and how they radiate. And so it's very hard to say. In general, you can say probably when you enhance the stiffness of the bass bar, that you will affect the modes that have a bending part along the bass bar. And that you will affect those more than other modes. So yeah. Probably that, but maybe George and Colin can predict better than me and what exactly it would do. It's yeah.
Okay, and the second question.
Yeah, for that I will go back to the presentation. So we were talking about the listeners, and you wanted to know about this 12CA violin or the 12CA and the 12CB.
Yes, the twin CA and twin CB.
Yes. So as you can see, I've tried to make these violins similar, and we saw that they were more similar than the others in our measurements, our radiation measurements. But here, indeed, you see that there is quite a big difference between the 12CA and the 12CB. Well, the 12CA, it was affected, of course, by the order, but still, when we look at 12CA the second time and 12CB, we see some differences. For example, 12CA is called sharp, while 12CB is not. So clearly, we have some different sound color between the two. And then, yeah, the question is where it comes from, and that's very difficult to say.
Yes, exactly.
Yes, because here we see that there is some difference between the modes, but it's not so very big. So I think, yeah, often we say audio engineers, when we talk about sharpness or brightness, it's more of a higher frequency thing. So what could be is that here you see some, so that's why I pointed this out, you see some small differences around 2000 Hertz and between 3,000 and 4,000 Hertz. Perhaps this could be an accidental difference in setup or some other accidental thing that I did in the making. I don't know, I'm not a robot. So these are not perfectly identical. So perhaps there is something here that could explain the difference. If it would be the other way around.
Did you make them together in the same time? Did you make them together?
Well, a few days apart, but in series.
Yeah, it's the same, yes. Okay.
Mm-hmm. Well, this is also due to my making method. So you see that I use the infusion process. There are other ways to make carbon fiber instruments, which may end up with more of the same, which are closer together. Also, it could be that there is some difference accidentally in the setup. Maybe I put a little bit more tension on the sound post, or there is some other difference. But that's hard, of course, to know what accidental difference you made between two violins. It's hard.
Okay, okay. Thank you very much.
You're welcome.
Sorry, may I add something?
Wait, Dietmar. John was first, but
it was exactly to this discussion right now.
Okay, it's just like he's gone anyway. No, it's just like
that's a short thing. Between CB and CA, there was a difference in the weight.
Yes, also yes.
And I think that might be the cause why there is a difference in sound. Because for the second one, I guess, which was a little bit more heavyweight, there could have been more resin. Resin does a lot to damping. Mm-hmm. That could affect the sound.
Yeah, it could be.
I'm quite sure, because that's something I discovered recently.
Yes, but when we do look, so the weight difference, I think you're definitely onto something. It could be important. The damping of between the 12CA and the 12CB, when we look at the modal analysis of the signature modes, there's not really a significant difference. So the A0, the B1, the etc., the damping that we measure is actually similar. So based on that, we cannot really say that 12CB has more damping than 12CA. Perhaps in these higher frequencies, it's different. But I think definitely the weight could be a difference. Because when we look at, for example, the UD Flex violin, which was the very heavy weight, we saw that as we went up in frequencies, it was very low in response. So maybe, but yeah, that's not really a scientific conclusion again. It could be that 12CA, it was 3 grams or 4 grams lighter, that this difference made the violin sound a little bit different. But here we're in a very gray area where it's hard to make conclusions, definitely based on just 2 instruments. So yeah, definitely.
Maybe even the carbon fibers were different.
Well, the carbon fiber used came from the same producer. And well, there's a lot less variability in carbon fiber than in wooden carbon fiber. So that's a very small chance.
How do you explain the increase in weight?
Carbon fiber, but that's rather small chance that this is the case.
The increase in weight, is it probably because of greater absorption of the resin in the fibers?
No, it's due to the infusion process. So you have a vacuum you have an inlet and an outlet, and the resin flows from the inlet towards the outlet. But this process is done by hand. So I determine when I open one or close the other.
Okay, okay.
And so
it's a handcrafted instrument.
Yes, of course. This you saw in the video. So if I close one valve maybe half a minute sooner than I did with the other one, again, some accidental difference, maybe I pulled out more resin from one of the two, or I introduced more resin from the other. So probably this difference, because the amount of fibers that I put in are exactly the same. So it's probably the resin content, and probably this is due to the infusion.
It's nice to see that makers are still precious, regardless of the material used.
I think that's a compliment. So I'll I don't know.
Yes.
So yes, thank you.
Thank you, thank you.
Okay, John isn't back, so we will go for another question. I do have a question. I mean, I've already asked you this question. It's just like, it's nice that we discuss it publicly. Why did you...
I'm back, actually.
Ah, you're back, John. Okay, so can I ask my question, or do you want to ask it before you appear again?
I'm going to ask my question. I'm about to, the internet is very, very unstable, and this is so I'll try now while I still can.
Yes, ask a question.
And okay, I'll just say I just let people know that I did slow work on bicycle and very large wind turbine blades, actually based off of instrument work. I posted one of the papers. The key piece there is that we worked on developing engineering constants for wood, carbon, and other laminates. So to actually be able to do modeling with. Here's an example of some of the bicycles that I've been working on. So I'll be very quick. But the question is for Tim, what material that intrigued you the most as a maker? What's the material that you would love to go, oh yes, this is really interesting. This is what I really want to keep running with from an innovation perspective.
Definitely. Difficult question again, because actually I really like the variety that these composite materials offer. And the fact that I can, depending on the question of the musician, I can make an instrument which sounds different using a different fiber. That being said, so I don't really want to pinpoint one, but that being said, I'm really drawn to the flax fiber. So this flax fiber, why? Because actually I'm here from Belgium, and flax fiber is native to here. We have actually our industrial revolution was in the beginning largely based on flax fibers. Over 70% of the flax fibers worldwide are grown in Belgium, the Netherlands, and the north of France. So it's extremely local to here. And also my great-grandfather actually worked in the flax fiber industry. So of course you can imagine that there is some emotional attachment to the fiber. And also because it surprised me so much, because in theory, it would not be a good sound radiator, and we actually saw it in the measurements. It's not very loud, but actually many listeners and players really like it, especially because it's so different. So because it's very warm, it's very round. It's not an instrument that you need to go on a big stage with and play a huge concert in front of a huge hall. It's not the instrument for that. But for pop musicians, for recordings, for people playing at home and just wanting to make a nice sound, they really like this instrument. So the flax fiber is something really I would like to continue with. Also the ecological aspect, of course, it's a lot less energy intensive than carbon fiber and glass fiber. Carbon fiber is quite energy intensive to make, while flax fiber is, well, very low energy. It just grows and they do some things with it. So yeah.
Yeah, that's actually a good transition with one of the questions I wanted to ask you. Is like, especially knowing you and your point of view of what's happening in the world and everything, I'm a bit surprised that you actually try to work with carbon fiber, which is not ecological at all. So can you discuss a bit this aspect of, like, I think that that was on the advantage of being a maker, is you work with wood, which is, of course, if it's coming from a renewable source, and we have to be careful with trees, but at least it's something very natural and very ecological if we use them properly. And so what is the idea of now, with all the problems we have and climate change and everything, what's the idea of working with carbon fiber?
Also a very good question. Yeah, well, the idea why I focused on composite materials was because they're also very durable. And so you do have an issue that I have not made these calculations, but you could argue that if you make one carbon fiber violin, a study violin, let's say, and it's extremely durable and it gets passed around for centuries, it might be more durable than a Chinese-made wooden violin. There are also good ones, but the cheap student ones that you buy for 50 euros, which we ship all over the world constantly. So in that case, my focus first was on durability. Of course, the carbon fiber aspect was because there was the most research available on it, and because there were already instruments being made out of carbon fiber, also violins and cellos. So I wanted to really start from there, and then we could branch outwards. So you saw that with the violins, we made only carbon fiber mostly, and then the one violin with the flex fiber. In the cellos, we have one carbon fiber, one glass fiber, and one flex fiber cello. So already we're branching out, but the idea was that we start from what we know that works, and based on what we learned there, we could adjust to other things. So for example, with the flex fiber, if we want to make it louder, we could think about adding a core material like the sandwich construction to it to make it louder. But that's an insight that we have had because of the carbon fiber experiments. So we very much really wanted to get some theoretical insights first from a research perspective. I will not be the person who starts a company and makes many carbon fiber violins and starts to sell it. I prefer to be a maker who makes instruments on order and to a certain musician's taste. So yeah.
Okay, and my other question was about the fact that why you didn't actually made a wooden back and ribs and just change the soundboards?
Well, because it would be very hard to do perceptional tests with it. So the idea was that we made these 6 violins and we could change between them very rapidly on stage. So we could have a listening and playing tests quite easily, and that these instruments would then also be available for musicians and composers if they wanted to use them. So many of these violins during the research have been on loan to musicians to be used. And if I have only one back side, etc., and we change the top plate, we also introduced many variables. Do we glue it again in exactly the same place? Things like this.
Yeah, no, sorry, I was thinking of having one back and a set of ribs for each violin. I know it has a problem of making them reliably enough, but you can see that you didn't manage to make them reliably either. You know, the tweeds and tweeds are different. So
actually, the difference between the back and the sides and the neck was a lot smaller in our production process than with the 2 soundboards. So it was okay. But yeah, the idea was when you go to wood, you have the same problem. You have the variability in the wood, which you know from the Bilbao project it's very hard to find wood which has the same characteristics. So we wanted to avoid that. And also, I'm a maker, I don't feel confident enough that I can say that I can produce 6 ribs and backs and necks consistently the same through the conventional making method. While with these molds, they sort of ensure that all of the dimensions are exactly the same each time. So for me, I felt more confident in making sure that this was not going to be a variable that we introduce accidentally to keep it all the same carbon fiber ones instead of making it wood.
Dimitri?
Yeah, Tim, thank you very much for your work and sharing. But I guess Claudia was asking, why don't you make just one back and one set of ribs and just changing the top plate in order to make 6 sets of ribs and backs? No?
What? So wait.
That was not exactly my question, because I know that if you do this, you have the gluing problem. Plus, that means that you don't have all the instruments available at the same time.
Ah, got you. Okay, thank you. So
that's a downside.
My question was, and you started to answer it a bit already, that it's very subjective, but in general, can you, in your opinion, why like the UD Flex violin was most liked and Sandwich and Wheel CA violins were not so much liked by people? Was it due to particular mode frequencies or their relationships, or due to particular material properties?
I think the Flex violin was mostly favored because of its sound color, in the case of the listeners, because in the solo condition, the projection and the loudness of the instrument was less important. And so the sound color was really important for them. And they just listened to many violins. And in my personal opinion, a violin in solo condition can sometimes be a bit hard to listen to. And this Flex violin, in an orchestra, it works great as a solo instrument, but solo, it's very high frequency. This Flex violin, makes it rounder, warmer. Maybe it has something to do with our taste in music, and that many people favor sounds that are warm and round. Like, for example, if you listen to the radio, here in Belgium, we have a classical radio, and the people talk with this very warm voice over the radio. And it's very comforting to us. And I think, in a way, the Flex violin maybe did the same, that it was a sound color which was very comforting to people. And for this particular piece, in this particular context, worked very well. Of course, if you change the context, if you go to a solo with an orchestra, etc., a different violin might be preferred, and probably will be.
Yeah, makes sense. But how all those things that you described look on spectrum?
Mm-hmm. So in the unidirectional Flex violin, we see that the modes are all quite low in frequency, and that actually the response is less at higher frequencies. So probably the warmth, the roundness of the sound is a combination of those, so that the signature modes are all quite low in frequency, and then the higher frequencies, they're less in the spectra that we hear.
Yeah, got you. Thank you. We'll go back later and check the spectrums. Thanks.
Thank you.
Yeah, I like your conclusion about the fact that in the end, it's something artistic. And so maybe just not the sound plays a role in the context. And so you said that, the glass fiber cello is maybe not the most attractive in terms of sound, but it shows them more. And that reminds me a paper about the fact there is difference and sometimes even contradiction between your evaluation when you actually do a separate evaluation or a joint evaluation. So you go to a shop, you want to buy a pair of loudspeakers, and you have this very fancy, nice design, it's a very beautiful design loudspeakers, and the sound is good, really good, but it's really attractive as well as a beautiful object. And you have these other loudspeakers, which are even better in terms of sound, but looks like big and massive, and you feel like, oh. And you listen to the two and you feel like, well, it's a pair of loudspeakers that should really give the advantage to the one that sounds really good. So even if they look less nice because you're buying loudspeakers. So you buy this pair of loudspeakers and you go home, you put them, and then you forget about the difference with the other ones. But what you see is that they look ugly in your living room. And then you go back to the shop and change for the other pair, which, okay, maybe slightly less good when you compare them. But when you arrive home, they look nice and you don't really remember the other ones which were a bit better. So, yeah. So that's probably what's happening with your cello. Okay, it sounds less good, but it looks really attractive. And now we'd like to finish with you showing us a video of this with the light.
Yes, because that's what I would like to say is...
Yes. Because it's really attractive, and I can imagine that now the purpose of this cello is to make music, but in an artistic context, which is just about sound, but as well visual and
Yeah, yes, definitely. And we've had musicians who actually put a spotlight under the glass fiber cello, which completely lights it up and then draws all the attention to it. So definitely the visual aspect is very important. And I think all violin makers know this just because of the varnish. An instrument with a horrible looking varnish will not sell. And an instrument that has a very nice varnish, maybe antiqued, it will sell easier. So I think many people really know this already. I've already posted the YouTube link just so people in the chat can check it out. If the audio connection would not be good or anything, you can listen to it yourself. So a little bit of context is just that there were a pianist and a cellist, and they wanted to record a piece by a Japanese composer called Takemitsu. And he wrote a piece, a duet, for cello and piano, in which he sort of does a crossover between the orchestral sound of Western culture and the more sound that they use in Japanese music. And so for that, they came to me to look for a cello which had a different sound color that really emphasizes this fact. So they wanted in the piano, the orchestral Western sound, and in the cello, they wanted more of a, Japanese, in a way, sounding instrument. So I've posted it here, and you can see it. So I will share it with you in a minute. The idea is that although this cello's sound is very different from a conventional one, it is artistically, according to these musicians, and I think it's the case as well, very well suited for this particular piece of music. But so I will let you be the judge of that yourself. So I will share my screen again. So here you see it. So it is on YouTube. You can look at it for Takemitsu, the Orient for cello and piano, by Lucas Hesman. He's the pianist. And so I will share it with you now.
you.